Hello, so welcome to Math2526. So in this class, we will continue to talk about many sample problem. So many sample problem, a typical example just like this. Like we have 4 classes, and we want to, so it seems class 1 perform better than other class, right? So class 1's average is 84, other class average is 81, 82, and 80. So it seems class 1 perform better than other class. But we wanted to check significance, right? So our question is, can we say class 1 performs significantly better than other class? So it comes out that's a question just like that. We have evidence. So we want to check the evidence strength of the significance of evidence. So like whether this evidence strong enough, right? So we will check the significance of the evidence. Okay. So our purpose, like suppose like I teach a class 1, so my purpose is wanted to say my class perform better than other class, right? But before I can say that, I need to check whether there is no difference, or there is no much difference among those 4 sections. So if there is no much difference, then we cannot say a class 1 is better than class 2, or class 1 better than others, or we don't need to compare those classes, right? We say basically, essentially, because they are quite the same. So we say, oh, this is better than other one is meaningless, right? So at first we need to check this. So we convert such a problem as hypothesis testing problem, right? So HO is mu1, mu2, mu3, mu4 all equal. So this means no much difference among those 4 classes. So HA have some difference, but the HA simply say not HO. Maybe like mu1, mu2 are same, but mu3, mu4 not the same, right? Okay. So if HO is true, then we can stop a comparison. If HO is not true, if we believe like for these 4 classes have difference, then we need to check a detail, like where the difference come from. Maybe like let's say class 2, class 4 maybe quite the same, 80, 81 are quite the same, but class 1 and class 4 they have some significant difference, like that, right? Okay. So for such testing, the test statistic is that. So we need to find this some cut point. So we call this a test statistic. So like find, so this suppose this is 0. So we want to find the cut point or test statistic. Then we want to check this number is a big number or small number. Big or small. So if this number is a big number, we can say the difference is big. And the distance between like for these two numbers, their distance is big. So if this number is small, then we say, oh, difference is small, and then the difference is not so significant. Okay. So for ANOVA test, the test statistic is thus F value. So we call F value. So the formula is thus, like S is G over degree of freedom, S is E over degree of freedom, right? So at the first step, we let's determine those degree of freedoms. Okay, so degree of freedom for numerator or degree of freedom for S is G. So remember the S is G is we just compare 4 groups, like group 1, group 2, group 3, group 4. And we assume in this direction no difference, right? So this means those numbers the same. So class 1 is, so those numbers just all numbers the same. So just we represent data by average. So just like class 1, each one's exam score is 84. Right? So here 81, class 2, 81, right? 81, and so class 3 is 82. So 82, and here 80. Okay, so the data looks like that. So we can say that in this direction, no difference. The only difference, the variance, just come from this way, right? So this is SSG. So this is SSG. Okay. So for such data, we say essentially we have 4 different numbers: 84, 81, 82, 80, right? So the degree of freedom is 3. So we have 4 numbers, n minus 1, 3. Okay. So then how can we determine degree of freedom in denominator df2? So we say total degree of freedom is n minus 1. So here, what is n? N, we just put those 4 classes together. So here, let's say what is n? So we say so here total. So add them up, we say it is students, right? So here total means we cannot add them up, right? So only total students 8. So this is n is 88. We put the 4 classes together. So we have 88 students. Okay, so the degree of freedom, total degree of freedom is 87. Okay. Okay, so we know there's a degree of freedom. So 87, we put this 87. So this split into 2 parts. This is 3. So then this should be 84, right? So degree of freedom 84. Also, we can use the formula n minus k, right? 84. But maybe we just this is maybe use this is more easy to understand, right? Just equal df1 plus df2, right? Total degree of freedom. We also split total degree of freedom into 2 parts. Okay, so for this f values, or df1 is 3, df2 is 84. So to find this f value, we need to find SSG, SSE. Okay, so what is ACG? So remember ACG, I repeated. Okay. What is ACG? So we say ACG is just like data like this. Those data, we want to find ACT for those kinds of data. 84, 84, 84, 84, 81, 81, 81, 81, like this. Okay, so this ACG is equal each number minus their average. So we need to find average for those numbers. So this average is just an average exam score for all classes. Average for all. So let's say we want to find average for total here. Average for these 4 classes. So this average equal, we can say like equal 84, 84, how many 84? Or 25, 84, right? Yeah, 25, 84, so 25 multiplied 84, and how many 81, 81? How many is 20, 81? So this average for all is, we can say like equal 88, total student 88, then total points for there's 4 classes. Class 1 is 25 times 84, right? Plus for class 2, class 2, how many? 81, 81. How many 81? We have 20, 81, right? So 20, 81, and like 20 multiplied 81. So this values for all should be calculated this way. So we also can understand that like this average is just the weighted average for those class averages. So we have average 84, 81, let's say 84, 81, 82, 80, right? So we have this 4 averages. Okay. So average for all is a weighted average for those 4 averages. Weighted on what? Weighted on class size or number of students. So we can say like this equal 25 times 84, 20 times 81, so 22 times 82, 21 times 80. So divided by totally, so totally is 88. So use this, right? So like 84. So weighted by student number like 22. So here totally, right? Just like that. So 81. So here multiply 20. So total weight is 25 plus 20, so 88. Okay, so we find this is average for all. So we call this average as a grand average. Okay. So here we have 5 averages. Average for each class. We have 4 averages, and then average for all. Okay. So we know SSG equals those numbers minus this average square. So we can find SSG equal 84 minus this square. So 84 minus the square, 84 minus square, we have totally have 25 of those numbers, because 84, 84, 84, we have like 84, 84, 84. We have in class 1, we have 25, 84, right? And class 2 is 81 minus this square, so 81 minus 81, so we have 20 of those numbers. Okay, so here same way like for class 3, so 82, 82, so 82 minus the square, so multiply 22, and so 80 minus the square times 20. So ACSG, we have the formula, but I think we just understand those ideas. Right? So ACSG, remember this is most important. How can we get ACSG? Is just replace the data by group average. So here is just 81, 81. So just like the data like this, so how can find those ACST, right? Okay. So by calculate by Excel or calculate we find this number is this. Okay. Okay. So what is ACSE? So remember ACSE is suppose data like this, like class 1's data, class 2's data, class 3. And class 4. So ACSE, we just check this values in this direction. Okay, values in this direction. So for class 1, each number minus class average, then square. Okay, so we find this is just like the values for class 1. Like class 1's values, let's say, how can find this S1 square? How can find this values for class 1? So we use this, like summation, like each number minus average. So this average is class 1's average, right? So divide by n minus 1. Okay. So this ACSG in numerator part, the numerator part just ACSG is equal Sn minus 1 multiply S1 square. Right? So we say this part is just ACSE. So equal n minus 1 times s squared. Okay, so for class 1, like this values in this direction is this. This is this. Then class 2 is this. Right? So use the same formula, class 3, class 4. Okay, so from the table we know S1 square is S1 is 7. So here S1 is standard deviation. So values is 7 square. Okay, right. So 7 square. Okay, so here S1 square 7 square. Then multiply 24. Okay, n minus 1, right? So here this square multiply 20 minus 1, 19. So this square multiply n minus 1, so here n 22, so become 21. Okay, so here 21 minus 1 become 20. Okay, so this is ACSE. Okay, so with this ACSE, we can find f value. So this divided by 3, df1 3, the df2 84. Okay, so we find this f value equal that's 1.18. So now we want to check Okay, so this number is big number or small number? 1.18. So this is small or big number. So we need to check the cut point t star value. Okay, so let's say t star value. Okay, so check the t star. I'm sorry, f star. So use this number to make our judgment. This number to determine like this 1.1 is big number or small number. Okay, so now let's check F table. So F table we have 2 degree of freedom, right? So degree of freedom in numerator is 3, denominator is 84. Okay, so let's check F table. Okay, so degree of freedom in this numerator 3, right? Let's say degree of freedom is 3 and 84. Okay, so degree of the freedom 3, then 84. So let's say move down 84. So we do not have 84. 3. Yeah, 1, 2, 3, 3. So 84. So we just pick a close one. 84. So we have like 60, 120. 60, 120 is which one is closer? I think 60, right? 60. So I just pick this 60. Okay. Okay. So I just use this number. Okay. So this is 2.7581. So this number we call F star. F critical value. Okay, so then based on this, okay, so use this number to make our judgment. So let's say 2.7581, right? Okay, so this is 2.5781 or 2.7581 or 2.5. I don't remember. Let's check. 2.7581. Yeah, I'm sorry. 2.7581. Okay. Okay, so use this number as a cut point, like 2.7581. Okay, so we say, so those numbers, small number, those number we can say big number. So we use this as a standard. Okay, so we find over cut point 1.18 is here. So we can say this number is small. Okay, so then we can make our decision, right? So this number is small, means the difference is small. Okay, so we can go back to our question of this. So we can say those 4 classes, they do have some difference, but such a difference is not so significant. It's small. So we can answer the question, can we say class 1 perform significantly better than other class? At this level, we say no. Class 1, their performance quite the same with other classes. So we can say, even though we have some evidence, it seems like the data, it seems class 1 perform bad, but we can say this is actually is not perform bad. Looks bad, but actually not so bad. Not so bad. Okay. Okay. So we solve this problem. So there's a typical many sample problem, right? We compare several groups, several samples. So for each group, we have sample size, sample mean, sample standard deviation. So based on this, we can conduct a ANOVA test. Okay? Okay. So for ANOVA test, we just need to calculate the F value, then compare this F value with the F critical value. To compare these two numbers of F value with this value, like we have two F values, this test statistic F value with this critical value, then we can determine this our test statistic or what cut point is big or small. Right? Okay. So we say like so find F value. We just need those things like we need to know SSG, SSE, and their degree of freedom, right? Okay. So sometimes we should determine the degree of freedom, and so those SSG, SSEs, if the data come from ordinary data, those calculations are tedious. So we usually will use a computer to do that, computer software to do that. Okay, and like so here, if we know the we have the similar data, we can do some calculation. Yeah. Okay. So sometimes like this, like we say from compute, from some statistical software, we can find. We already know some. Then, based on this, I will ask you to find the F value, then make a decision. Okay, so let's check this problem. So at the first, the SSG. If we know SST, SSE, then SSG equal SST minus SSE, right? So this is ANOVA. ST equal SSG plus SSE, right? So here we can say, oh, this is so here this is easy, right? Okay, so this so if we know SST, SSE, then SSG equals this. 8, 4, 6, 7. So here a little bit of calculation, right? 6, 8, 9. So okay. So we say this equal 1, 6, 7, 8. So this is ANOVA. So ANOVA, you should remember ANOVA. So here is just equal SST. We split SST into two parts, right? SSG plus SSE. This is ANOVA. Okay. Okay. Then degree of freedom df1 is we just check how many groups we compare. Okay. So this is the k minus 1. So k is number of group. So let's say we compare 6 treatment. Okay, so here we just compare 6 group, right? So degree of freedom df1 in numerator is 5. Okay. So what is the degree of freedom for denominator df2? So we say equal just the n minus 1 total degree of freedom minus this df1. So this equal total degree of freedom n minus 1 minus 5. So what is n here? So what is n? N is total numbers. So let's check the problem. It says we compare 6 treatments or 6 drugs. Each has 20 patients. So like here 20 patients, right? Then 20 patients. So we compare the 6 group, right? So totally n is we have 6 group, each is 20. So n is equal 120, right? So this is actually 120 minus 6 equal 114. Okay, right? So we know the degree of freedom denominator is 114, numerate 5. So what is the f value? F value, let's say the f value equal, just use the formula, SSG over degree of freedom and SSE over its degree of freedom. So those 2 degree of freedom not the same, so we distinguish them. So here SSG, let's say SSG equals us, and the degree of freedom 5. We compare 6 groups, right? So there's 5. And this SSE, let's say, so what is SSE? Now SSE is this, like 6, 7, 8, 9. 6, 7, 8, 9. So over degree of freedom 114. Okay. So use calculate, so we can find this number, right? So you can use Excel to find this quickly. So for me, I use this calculate. I take a little bit of time, but anyway, let's do this. Okay, divide by 5. Okay, and 6, 7, 8, 9 divided by 114. Okay, so it's equal 5.63. Okay, so this is our cutoff point. Then we need to determine p-value less than 0.005 or larger than 0.005, or we need to determine this number is big number, small number. So we can check this F star, critical value. So here degree of freedom is 5 and 114. So check this F table. So okay. Okay, so here the time numerate degree of freedom 5. So here this times 5, 114, right? So 5 and 114. So here again 114. So we just pick a close one. We just pick 120, right? Okay, 120. So 5. So here first one 1, 2, 3, 4, 5. So this number. Okay. So this time this f critical value f star equal 2.2899. Okay, so 2.2899. Okay. So let me write it down here. Okay. So 2.2899. So we can say this f is big number, right? So we start just like that. We here 0. So here's 2.2899. We use this number to determine small or big. So those numbers small number, those number big number. Okay. So over number 5.63 is, so we can say this is big number. Okay. So this is big number, means these 6 groups have a difference, have a significant difference. Their difference is big. Or we can say there's 6 treatments have significant difference, right? Or we can say that treatments are not quite the same. They have a difference. So can we conclude that these treatments are essentially quite the same? We say no, they have significant difference, right? Okay. So we say make a decision. So we say we can use this way, just make the decision, means just determine this cut point is big number, small number. So before we say make a decision based on the p-value, like p-value less than alpha HA, larger than alpha HO. So these 2 methods actually the same. So here, what is the p-value? Here, let's say if we want to determine compare p-value larger than 0.005 or less than 0.005. So what is this this number meanings? So this number actually is, like suppose this is a distribution, like if distribution, so here's 0, and so this point here is 0.005. So this f star is just the cut point for 0.005. Okay. So our cut point is here 5.63. So this part is our p-value. Okay. So from the graph we can say that the p-value is less than 0.005, right? So conclusion, according to our conclusion, so conclusion is no. Okay, why? Conclusion HA, right? So what the HA means here? HA means have difference or have significant difference, right? Okay, so today's topic is continued for many sample problem, many sample ANOVA test, or many sample t-test, or if test. So we finish this topic. Okay, so we can stop here. Okay, so thank you for watching.